You're gathering roots in a savanna 80,000 years ago. The grass is tall, and a single footstep triggers a lightning-fast strike at your ankle. You've just been bitten by a black mamba. For 100 million years, this species and others like it have been perfecting a combination of aggressive speed and highly specialized chemical weaponry. Early humans were uniquely vulnerable to this threat. We don't have the thick, impenetrable skin of a honey badger, nor do our cells possess the molecular venom resistance of a mongoose. We are slow, soft targets. This animation illustrates the biological reality of a full envenomation. The neurotoxin rapidly invades the bloodstream, shutting down the nervous system, paralyzing the diaphragm, and causing suffocation in under 20 minutes. There are no hospitals, and antivenom does not exist. Given those facts, a bite should have been a 100% fatal event. Every encounter was a mathematical death sentence. So, how did early hominids survive long enough to populate the Earth? The first line of defense actually engages before the snake even moves. Humans evolved a highly specialized visual alarm system. Looking at this brain cross-section, we observe snake detection theory. The pulvinar region contains neurons hardwired to detect S-curves and coiled patterns. This signal path bypasses conscious thought entirely, triggering an immediate physical flinch before you even realize what you're seeing. This created a brutal evolutionary filter. Ancient hominids lacking this fast pattern recognition were continually killed off. Only those carrying this specific attentional bias survived to pass on their genes. We did not survive by learning to fight these predators. The constant lethal pressure of snakes directly redesigned the architecture of the human eye and brain. But visual alarms sometimes fail. When an actual strike occurs, human survival often depended on a biological anomaly called a dry bite, a scenario where the fangs break the skin but inject absolutely zero venom. This chart maps a snake's energy budget. Synthesizing venom carries a severe metabolic cost, requiring massive calories and time to refill. Since a human is too large to consume, the snake runs a rapid calculation, often delivering a defensive warning jab to conserve venom. This physiological math accidentally created ancient medical myths. A hunter receives a dry bite, chews on a random local leaf, recovers perfectly from the strike, and confidently passes down the belief that the plant cured them. In reality, thousands of humans walked away from these encounters simply because the reptile decided their body was not worth the biological expense. If the snake did inject a full lethal dose, humans relied on deeply trusted tribal treatments. They would tightly bind the limb with cords or cut the wound to extract the poison. These confident traditions were catastrophic. Tying off a limb chokes the blood flow, usually accelerating irreversible tissue necrosis, or inviting a lethal infection that killed the patient faster than the venom alone. This graphic illustrates the true biological defense. Surviving envenomation is a strict physiological equation. Venom dose weighed against victim mass and time. A healthy liver and kidneys can filter out venom proteins. They simply need enough time to break the molecules down. Time was provided by the community. Anthropologists documenting the modern Hadza people witnessed a hunter severely bitten by a puff adder. His community stopped foraging entirely. They carried his body, forced constant hydration to keep kidneys flushing, and kept him awake and talking for 3 full days. He lived. Surviving a lethal dose was rarely an individual triumph. The tribe functioned as an external life support system, pooling resources to outlast the venom's clock. After 300,000 years of adaptation and communal care, the dynamic has inverted. Humans now synthesize antivenom in laboratories, map reptilian genomes, and through habitat expansion, stand as the greatest threat to snake populations. Yet, walk down a quiet trail today and step near a curved piece of wood, you'll likely experience a sudden, violent physical flinch. That involuntary reaction is a profound biological artifact. It's a pre-conscious survival circuit operating inside you, firing identical signals to the ones that protected early hominids in the tall grass. That instinctual jolt is an invisible inheritance. It was paid for in blood by ancestors who learned to spot danger a half-second sooner, and by the communities that refused to let them die alone.